Okay. Welcome PCS members and friends to our PCS IBS seminar. Today we are happy to host Professor Nicoló Lo Piparo from Okinawa Institute of Science and Technology from Japan. And our scientific host today is Dominic, who will introduce our speaker.
Okay. It is my pleasure to introduce Dr. Nicoló Lo Piparo. He came to us from OIST in Okinawa about this bio. He studied renormalization group applied to non-gauge gauge theory during his master's in Italy in Catania. But during his PhD, he's completely changed the topic and started studying quantum key distribution at the University of Leeds. And after finishing his PhD, he moved to Japan, where he won a Japanese scholarship JSPS and moved to the National Institute of Informatics. He continued his work on the quantum key distribution and developed a novel system to reduce the number of resources in quantum error correction code. And since 2021, he's a staff scientist at the Okinawa Institute of Science and Technology, as I said, OIST, where he continues to study these quantum key distribution protocols to make the quantum internet a reality and supervises several students. The floor is yours, Nicoló.
Thank you. Thank you very much for the nice introduction, and thanks everybody for being here today. So yes, Dominic said, I'm Nicoló Lo Piparo, and today I'm going to talk about a type of quantum networks that have been working since like 2 years. Then the main, let's say the hard job has been made by this PhD student. So I want to give credit to him, Peiji Lee. And it is also work done in collaboration with Bill Monroe. And Kanemoto is the PI of the unit I belong, which is this quantum information science technology unit. And Bill Monroe actually is working as a PI on another unit, a quantum engineer and design unit that just recently started at OIST. So OIST is a very big community. There are many units in different type of fields, so several units. And sometimes we exchange information and we work together. So let me go to the outline. So, okay, so I'm going to talk about quantum networks just as an introduction. And but why I want to give you a bit of motivation why we are doing this. I mean, it's for the glory or is for other reasons. Actually, we think that in the future, in the near future, quantum technologies can have a higher performance compared to classical technologies, at least in theory. I mean, I belong to a theorist group, but we have to face also the challenges when we try to implement these technologies. And so, in particular, we focus on quantum communication systems. So, if we have parties separated by large distances and they want to communicate, what are the quantum systems that allows this? So how do we do this? How we can reach this quantum communication? And on Earth, the best way to do it is using quantum repeaters. So I'm going to say something about that and also different types of quantum repeaters. I'm going to describe what are the good things and the bad things of using this type of systems. And then after all that, I will describe more into details what are the systems that we studied, we analyzed, particularly these, I mean, maybe some of you are already familiar with cut states and these other new type of codes called the rotational symmetric bosonic codes and cavity-QED. And QKD, because of course, I mean, as Dominic said, I've been working on QKD quite a long time, so it's always that. And then at the end, I will just say something about some experiments that have been done to implement this type of systems. Already this system could be kind of reality. So let me introduce saying so quantum networks, just a short introduction. I mean, as you can see here from these pictures, the goal is to connect the different cities all around the world. I mean, this is just a map of Europe, but Of course, the final goal is to connect different cities in different parts of the world. And then, depending on the goal of the quantum networks, the main two goals are basically quantum computation or quantum communication. And then to achieve this type of goal, we require different type of resources. In particular, for quantum computation, for quantum computation, we need to distribute basically qubit. And to do that, I mean, of course, the final goal is to create a cluster of quantum computers in such a way the power of this cluster could be quite big, right? Like even in the classical work, it works this way, right? You put together many computers to enhance the final power. And the other way to, the other task, which actually is the one that I'm going to talk today more into details, is using quantum networks for communication. I mean, at the end of quantum networks is always a bunch of nodes connected by these edges. So in the quantum networks used for communication, basically you have to think of these edges like entangled pairs. So we want to, in the quantum communication world, we want to exchange entangled state between the different nodes. Normally, this entangled state carries some information which is encoded into photons, because as we know, they are quite fast. Photons that can travel over optical fibers, but also over free space. So the ultimate goal of quantum communication, as I said, is to distribute entangled pair. And to do that, I mean, already there is already something has been done in the past. For example, we have in Tokyo, we have the QED network, and just in the city of Tokyo. It's a network. I mean, it's not that it cannot distribute entangled states over large distances, but it has already been implemented for a simple task of QED. Also in 2017, China opened a 2,000 communication line, a 2,000 kilometers communication line between Beijing and Shanghai. And they made a kind of video call using satellites. And more recently, in 2020, there was this amazing work done by some of these people are my friends, Raju, Neil, Maria. They did, basically, they implemented a teleportation protocol over 44 kilometers, and that's quite a big achievement. So also in US, they are focusing on creating these quantum networks. The problem now is that this quantum network, as I said, we want to connect different cities, right? So for example, here we say like 2,000 kilometers, but it could be even 1,000 or a bit less. The problem is that these photons traveling over these large distances could be, they have to face many problems, many errors, especially channel loss. Channel loss is the main thing that the main obstacle to the real implementation of these of the network. Normally, the information or the rate we can exchange this entangled state decay exponentially with the distance. So as you can see, exponential decay doesn't allow to actually distribute the entangled pair over very large distances. So the main way we address this issue is using the so-called quantum repeater. So let me introduce briefly what these quantum repeaters are. And
so may I ask you one question? In these papers that you mentioned, did they use a single photon or a bunch of photons?
You mean like the teleportation system, this one?
Actually, I don't see. I don't know exactly the difference between these two papers. For example, the upper one.
Yeah. So normally the ideal case is using single photons to perform this protocol. That's the ideal case. However, single photons is very hard to produce. So normally there are different other ways. Normally you use attenuated coherent pulse laser. So normally laser with you tune your system in such a way that you try to minimize the double photon component. So all these systems, especially in QED, are very sensitive for multiple photon components. That means that, as I say, that we want to create a correlation. Entangled state is basically a quantum correlation between two parties, right?
Mhm.
So when we have multiple photons in our source, destroy this correlation. That means that the rate, for example, or the fidelity of our final states is really bad, and actually sometimes it's actually useless. So in this case, they use a coherence source, but also SPDC, like spontaneous parametric conversion.
Mhm.
Again, even with the SPDC, you have a non-zero probability of creating multiple pairs. So one of the main challenges is this, but they try to minimize these type of errors. And as I said, that's why it's kind of astonishing that they managed to do this teleportation protocol over 44 kilometers. However, as I say, the final goal is to reach thousands of kilometers. So in this case, it's very challenging. The way, as I was saying, by the way, please interrupt me anytime.
I also
Yes.
have some naive question. What is the rate of success for this teleportation for 44 kilometers?
The rate of success, I can't recall at the moment, but it was, I think, a few kilobits per second. Something like this. I'm not that sure 100%. I have to double check. But anyway, it's a very good question because the rate is something that I'm going to talk in the next slides, and that actually is the main figure of merit in protocols like this, especially in QK. So let me first introduce a quantum repeater protocol. Maybe most of you already know what it is. So as I said, we have two parties, Alice and Bob, and normally they are separated by a large distance L. So as I said, the rate decays exponentially with the distance, so it's going to be a really big problem. How can we address this issue? Okay, in the quantum repeater, basically, we split the channel into smaller segments, L0. This is just an example, right? We can split even more of these segments. The smaller, the farther we can go. And we distribute entangled states over this elementary distance. And we store our states into this QM. These are just quantum memories. So basically, we have an entangled state shared between these two quantum memories, an entangled state here, here, and here. And then, okay, so this means that basically now the light must travel over L0. So in this case, you have an advantage from this point of view. And then we want to extend this entangled state over large distances, and this could be done by performing so-called Bell state measurement. So Bell state measurement is just basically a measurement on one of the 4 Bell states. And this could be done, let's say easily, just using, for example, beam splitter and photon detectors. It's not super complicated, but it could be done. It could be performed quite well. And basically, this Bell state measurement has the effect to extend, as I say, the Bell state over larger distances. So now these two quantum memories will be entangled, and you can perform this type of measurement as many times as you want until you reach your desired distance between Alice and Bob. So, initially, yes, please.
So in this load measurement, you have 4 outcomes, right?
Yes.
And I wonder, do you need to post-select to get to the entangled pair?
Yes, normally the post-selection is made, so sometimes depending on how you are performing the Bell state measurement, you have a click pattern. So depending, you have your photon detectors, and depending which detector will click, will tell you have this Bell state measurement or another Bell state measurement. If you, for example, you might have a no click, and this is already basically no click, it means that your Bell state measurement was unsuccessful. So that's actually also another reason why we need memories. We need memories because, for example, let's say this entangled state, let's say this Bell state measurement has been is successful. So already we have these two memories here. We have these two memories entangled, but this Bell state measurement is not successful. So what it means is that we have to do it again. So that means we have to again distribute the entangled state over elementary distance, wait until these two are entangled, and then performing the Bell state measurement.
Yeah, but you change the state by making a measurement, right? So it's a different entangled state after you get some outcome.
Yes.
So do you do some correction unitary afterwards?
Yes, you can correct locally because, of course, these two quantum memories are in the same station. So you can correct applying like a Pauli operation in
I see.
exchange like Z or X Pauli. And you obtain, but it's not that relevant anyway, because the ultimate goal at the end is to, and at the end you will have one of the four Bell state between Alice and Bob, and that is enough to carry on with any QKD implementation. So as long as like they know which Bell state they have, they can, for example, target a secret key in a QKD scenario.
I see. So there will be like extra wire carrying that classical information?
Yes, the classical information will be required in a kind of an improved version of this. But yes, I mean, let's say they do this many times. At the very end, these, for example, this station can communicate to Alice and Bob what are their results in such a way they know. For example, first round, we got this type of a Bell state, second round, this type. So it's just an information that could be given to Alice Bomb at the very end of the program.
But wouldn't this classical communication be a security risk?
No, because the way it works is that knowing what are the Bell state doesn't know. So the Bell state could be 0, 0 plus 1, 1, right? But only Alice and Bob knows which are the state, if it could be 0 or 1. If we have another part in between, the important thing is that that they have this type of correlation. That's what it is. Because the way they could, the only thing that they have to do is they have the entangled state, and they could do, for example, by performing like checking the Bell's inequality, right? So if they see that they violate the Bell inequality that occurs, they can say, we still have this entanglement. As long as like let's say the quantumness of their system is preserved, this guarantee that they can establish a secret.
So just knowing the classical outcomes on those repeaters doesn't
give away any information enough to reconstruct the final.
Okay, thanks.
So in this case, whenever you have the measurement success, you know that the information transfer. But if the measurement not success, the information not transferred, right?
Yes.
And then you say that you need a quantum memory for that.
Yes.
When we know that we have the no cloning theorem, how can you prepare the memory?
Well, normally the memory is the memory are so you initialize your memory, right? For example, in a superposition state, and then you distribute. So the memory are just matter qubit. So the information is transferred using photons. So normally this matter qubit could be a two-level system. And so what you're doing is you're transferring the information contained in your photons into the memory. So you're entangling your system with the memories. At the end, you can measure these photons, and basically you're entangled your memories.
And in this case, you need to have memory for every step, right? You need to have memory for every step of the sample, or you need memory for only for the first bit?
You need memory in each station. You need memory in each station. I mean, it's going to be more clear, actually. Let me go to the next slides where basically I'll show you in this case, it's just a simple distribution. I mean, you can assume also that, for example, kind of a perfect Bell state measurement is always 100% successful. In this case, you don't need to store your state. You just need distributing your entangled state and do the Bell state measurement when both arrive. But there is another protocol that is normally it's used for quantum repeater, which is called quantum purification. In that case, you definitely need quantum memories.
Excuse me, for non-experts, who makes Bell state measurement? What does it mean? Is it some third party does it, or?
Yeah, that's a good question. It's interesting. Like, so the thing is, like, you can produce a Bell state measurement, as I said before, with parametric down conversion. So, for example, we have a parametric down conversion in the middle and distribute your entangled state to the quantum memories. That could be a way, but there are many other ways you can do this. Even with a single photon source, there is a protocol called a single photon protocol that allows to distribute entangled state using just a beam splitter and photon detectors. So there are many ways you can create Bell states.
So it's just creation of Bell state.
Creation of Bell state, yes.
Because with measurement is kind of confusing.
The measurement is a projection. So let's say you have a 0, 0 plus 1, 1 and 0, 0 plus 1, 1 here.
Yeah.
You perform a Bell state measurement, which corresponds to a C naught plus Hadamard. Here, of course, in the state here. So you do C naught between this qubit and this qubit, then an Hadamard, and then you measure in the Z basis. These two memories you measure in Z basis. At the end, you will have 0, 0 plus 1, 1 between these two. If everything is ideal, because definitely these measurements, practically you use, as I say, photon detectors, you use beam splitter. These will introduce some errors in your system. So at the end, you will have your Bell state plus something else, vacuum terms, or maybe even the.
So what's going on with the error? You have to correct it, or
it's in the next slide.
Okay.
So yeah, thanks for that. Also allows me to introduce the next slide. So as you understood already, we have errors, right? Because these Bell state measurements are not perfect, are not ideal, and so we can introduce some errors. There are two main ways we can address these errors. One way is using quantum purification, which is basically, this is just a very simple scheme. Quantum purification is basically so what we need in this case, we have these two quantum memories here, right? And we create another, so we are using other quantum memories here. And then basically we perform, and we assume that, for example, we are storing our state. So we are storing our state for a certain time. So that means that our state could go to dephase, for example, or depolarization, right? So they are losing their information contained into the state. So let's assume we have, for example, the Bell state plus identity, right? Something like this. And here too, the same thing. So this, the purification protocol works in this way. We perform a C naught between these memories and these memories. Then we can perform an Hadamard on, so basically we rotate the state on both of these memories, and we measure we can measure these, the upper memory or the lower memory, it doesn't matter. At the end, the fidelity, the final fidelity of the state, which is basically the fidelity is how far is the final state from the initial one. I mean, it's given by this scalar product here, but the psi is, for example, one of the Bell state, is not normalized, by the way. What we get at the end is a state that has a slightly higher fidelity than the initial one. And this could be done, so basically this protocol is telling us that we are consuming some physical resources, because these are physical resources that we are using, as quantum memories. So the price we have to pay is using physical resources. But what we can get is a final entangled state between these memories, which has a slightly higher fidelity, or if you like, quality. So the final quality of this entangled state will be slightly higher. And you can extend, I mean, this, of course, this protocol, unfortunately, no, this protocol is not deterministic. It depends on the outcome of as I said, we have to measure, for example, these two memories. So we measure these two memories, we might have 4 possible outcomes, 0, 0, 0, 1, 1, 0, and 1, 1. And the cases that give us only higher fidelity are when the measurement is the same. So what it means is that there must be communication, right? Because this guy must say, I got this result, this outcome, and he say, I get this outcome. So when the outcomes are the same, the fidelity will be higher. But sometimes it's not, because as I said, it's probabilistic. So it will succeed with some probability. In other words, we have to take into account some communication time in this case, which it could be quite bad, because as I showed you in the previous slide, our ultimate goal is to distribute the entangled state all over the total distance. So at the end, basically, the communication time will scale with the total distance. It's, I mean, this type of protocol, let's say it's easier, it's kind of easy, but it consumes a lot of resources, and it takes time. It takes a bit of time. Therefore, there are other ways to improve this, and basically the other one, as far as I know, is using quantum error correction. With quantum error correction, is basically the main concept is to kind of encode our state. For example, in this case, let's say we are using a photon, and we can use a different degree of freedom. In this case, it's polarization. So we can say, for example, 0 corresponded to H polarized photon and 1 to vertical polarized photons. And we can do this like we can create a logic state, as you can see here, it's given by this tensor product. Maybe let me use it. So it's using by this tensor product here. So the main concept of quantum error correction is to start with a simple system, physical system, and then to add more and more, in this case, more photons. By the way, this is just an example of error correction called parity code. So in the parity code, you encode your logic state in this way. At the end, basically, what you're doing is instead of sending, let's say, alpha 0 plus beta 1, which is your information, like your encoded state, you're sending alpha 0 logic plus beta 1 logic, which is given by this expression. So basically, what's going on here is that we are, again, using resources, in this case, photons, to create a redundancy. So a more complicated state that can it's more resilient to some type of errors. Of course, there are many quantum error correction codes, and this is just an example, of course. Depending on the codes, some error correction code can correct, for example, losses, other can correct bit flip, and so on and so forth.
I'm sorry, I'm lost. I used to think that in order to make error correction code, you need a number of physical qubits for one logical qubit. And yeah. It looks here that you just operate with one of them, and it's enough to make error correction.
No, sorry, maybe I should have written, basically, this plus m is like a tensor product. So we have let's say 0, 0, 0. So we have many of photons here. In this state, which is, so we started with this one, right? And then in this state, we have m photons entangled with this state. So we have this 0, 0, 0 plus 1, 1, 1, like GZ state, for example. And then the same for 1. So one of
so how you create from one photon many excite many qubits?
Yeah, that's a very good question. Basically, normally you create this as you're performing a logic gate. So that's the hard part of our quantum error correction is for the encoding of your initial state. You need the logic gate between the qubits. So, for example, you start with a certain number initialized to 0, your qubit. Could be qubit, depending your error correction code, and then you perform some. Normally, there are CNOT gate between these qubits. So that's a very good question. That's a very good point, because in quantum error correction, what we need is that we need the ideal gates, ideal quantum gates. Changing the efficiency even slightly of these gates could mess. Of course, this is the ideal case, right? But if we include errors, of course, this initial state will be more messy, will contain some error. But the ideal case is just to use. So yes, as I said, basically we initialize our qubits and we perform some normally CNOT gate between the qubits. You can extend this also to qubit. It could work also, for example, the quantum Rees-Solomon code is another code that in that case you need qubits. This is one of the type of code. I mean, I just put it to. This allows me basically to introduce the next concept, which is the different type of quantum repeaters. Because so in this table, basically, this is a work done in 2016. Basically, in this work, they base on the fact that if you are using either quantum purification or quantum error correction, you can distinguish your quantum repeater in 3 generations. Okay, so we have, let's look at 2 types of errors, which are the main errors. One type is the loss error, and the other one is the operation error. loss errors normally in a quantum communication happen when we transmit our information over optical fiber. So for example, when we want to create our entangled state, as I say, we have to send our photons. So how can we, let's say, correct? How can we be aware that we created our entangled state? So for the first generation, this is done in a heralding way. So in fact, it's called heralding entanglement generation. As you can see here, heralding means that, for example, as you see here, Alice and Bob are sending their state to this middle station. And heralding means that we must have a click. So if this click, this guy will tell, yes, it clicked. So it means that the photon reach this station, so they can, eventually they will share an entangled state. That's why it's called heralding. And so that's the way the entanglement generation happens in the first generation. And then the first generation also included the entanglement purification protocol that I just explained. And then you can have a second generation and third generation. So for second generation, use the same way of distributing entanglement all over elementary distance. So again, in a heralding way, but the instead of doing entanglement purification, they do entanglement, they do a quantum error correction. So as you can see, second generation is, so address loss errors using the HEG and herald entanglement generation, but the to do the entanglement swap to extend the distance of this entangled pair. This is done using quantum error correction. And the third generation, which is actually the best, right? The best in terms of efficiency, use error correction for both things, for also addressing loss errors and operation errors. However, the gate efficiency of the third generation must be almost unity to work. So when we prepare this type of state, they must be basically perfect. And that's why of the reason why third generation is the best in terms of efficiency, but it's incredibly hard to implement.
So where do the repeaters come in the picture?
The repeater comes in the picture already. So basically, the repeater system is so you made your repeater system by, as I said in the previous slide, let me go back. So in the previous slide, you have a distributed entanglement all over elementary distance, right? What type of error you can have? Loss error. That's the error, right? The photons could be lost. So this entanglement distribution could be the loss error that you have during the entanglement distribution could be addressed in two ways. Either with this, as I said, heralded in a heralded way, that means there is somebody that says, yes, we have the click, so the photons arrived. Or encoding your system with this error correction. Basically, the encoding makes your system, your photon, your system, your information actually much more protected. So, for example, there are error correction code that can tolerate the loss of one photon or two photons. That means that when your state reached the other station, you can correct depending how many photons have you lost.
So these error corrections are happening at each repeater location?
Yeah, in each station, yes.
Okay.
And then, I mean, as I said, for example, in this case, let's assume we have this, the second part is the quantum purification, right? Because as I said, we have errors when we perform the Bell state measurement. So that means that this, for example, in this level, the entangled state between these two memories will be not an ideal entangled state, not a maximal entangled state, right? That will contain spurious terms. And so therefore you can increase the quality of this entangled state performing quantum purification, or again, quantum error correction. Of course, the quantum error correction is much more, require many more resources to do this.
So is it good to do it at every station, or is it enough to do it at Alice and Bob?
No, you have to do it at every station. Otherwise, the thing is, like when you perform your Bell state measurement, which basically this procedure called entanglement swapping, you are also forward your errors. So if you don't correct these errors, this will be also present. I mean, it can have other contribution for other Bell state measurement.
What about purification? Maybe purification could be done on ASB.
Purification makes the fidelity higher of your
Yes, but
entangled
do
state.
you also have to do purification at every station?
All the times you do your Bell state measurement,
Yes.
you purify your state, and then you do another Bell state measurement, you purify your state, each elementary link. That's the way it works.
Okay.
So basically, this distinction, I mean, this paper was quite good because at the end it kind of summarized the way we can implement, I mean, at least the generation of quantum repeaters. I mean, the reason I put it, this is still a kind of introduction. The reason I put it this is because the system that we analyze, I think it doesn't belong to any of these three, but has good things of the first generation, second generation, and third generation. That's why I wanted to talk about.
So I still wonder, can you do both quantum purification and quantum error correction?
Or it's not convenient. Because think about it, quantum communication, first of all, quantum purification, as I said, is a probabilistic, sorry, next slide. Quantum purification is a probabilistic thing, right? It's a probabilistic operation. What it means is that sometimes it doesn't, with some probability, it doesn't succeed. And what it means is it doesn't succeed. So, for example, let's say in this case, it doesn't succeed. So you have to keep, before doing the Bell state measurement, you have to store your state into these memories. This is actually the main reason why we are using memories, because at least for the first generation quantum repeater, it's probably doesn't succeed. So you have to keep in your state in these memories, but these memories are not ideal, right? So there must be some coherence time and some decoherence. So you have to include some decoherence time that will deteriorate the quality of your state. So it's not convenient. Why do we want to use both? Quantum error correction is better in terms of they are deterministic procedure. So if we can use quantum error correction, that means if we can have a very good gates, we don't need quantum purification. As well as we can do quantum error correction in both, like in the loss error and the quantum operation, we just are happy to use the third generation.
And the error correction always works?
Error correction is a deterministic. I mean, there is also, of course, a probability of success, but it's a deterministic event in terms of so like if you have, let's say, some number of resources, you know that this will occur. This will be successful. So it's you don't need the quantum communication in this case to acknowledge the result. If you have that type of result, you just know it worked.
Okay.
And then let me just shortly say how we can compare. So why we can say that, for example, something is better than, like one protocol is better than the other. The way we do this is just we assume that, for example, our quantum repeater is used, as I said, to distribute entangled state, as I said, and these entangled states are used in a QED scenario, in a QED protocol. For the ones who don't know QED, I'm going to go very fast here. Basically, we have, again, always two parties, Alice and Bob, and they want to share a secret key. And so this secret key can be used by Alice to encode her message and send it to Bob. However, in the middle, we have an eavesdropper, which is called Eve, that try to catch basically this key. And thanks to the law of quantum mechanics, we can, I mentioned before, for example, that as long as the quantumness contained in the entangled state is preserved, that means checking the Bell's inequality, they can be not 100% secure, but with some probability, they could eventually share a secret key. So basically, the good thing of QED is that you don't need computational power. Okay, you don't need a super big computer. You just rely on the basic law of quantum mechanics. Because as we know, if Eve tried to intercept the key, intercepting the key means making a measurement, right? Of the, for example, Alice and Bob are as I say, they're exchanging entangled state. So if Eve make a measurement, she will introduce some errors that could be eventually detected by Alice and Bob. And then, so the good thing here is that, so as I said, what we want to see to evaluate the performance of this repeater system is in a QED scenario, is the rate. So how fast Alice and Bob can exchange their secret key. And no, as I said before, if we have a direct link without quantum repeater, the rate will scale exponentially with the distance. So this will make the final rate really bad. As you can see here, for example, this dashed line here is telling you what's the rate versus the distance without quantum repeaters. When we add the quantum
rate is inverse time. What's the definition of the rate?
Yes, it's here. Sorry, sorry. So basically, the rate is defined as so this P tot is the total probability of getting the final state multiplied by this quantity, which is basically is 1 minus, this is the binomial entropy, the fidelity. So basically this quantity is, it's just a theoretical, it's a theoretical outcome. Of course, I'm not an expert, but basically what happens is like you assume like you have a channel, and in this channel you assume to have an eavesdropper that could make some type of measurement. At the end, what you get is basically this rate, but this rate, of course, you have to multiply with something that is less than 1, because it's like always Eve can always extract some information from the exchange states. So this basically this quantity takes into account the amount of key rate that you have to sacrifice, because you're assuming that there is always a leakage. So Eve can always intercept part of the keys. But normally the definition of the rate is this one, depending on the protocol, there could be other terms here, but it's always, let's say the probability of exchanging the entangled state multiplied by something that makes it smaller. Yes, that's basically the way we define the rate. And that's, as I said, the main figure of merit used to compare different protocols. And in the paper that I cited in the previous slide, actually, as a main figure of merit, they use the so-called cost function, which is basically the number of resources, of physical resources. They could be quantum memories, or it could be qubits, whatever you are using, right? Divided the rate. And then you can write this also per station, okay? So this is the total number of resources, and then you decompose per single station. And then the other, another way also is just dividing this cost function over the total distance. So this is actually the way we can compare different quantum repeaters. So either we calculate the rate, but of course, maybe we have that one protocol has a higher rate than another, but of course, how many qubits or how many quantum memories do we need, right? So this takes into account both.
What are units for the cost function? Is it dimensionless? It looks like L is in centimeters or what? What is elementary length?
It's a frequency because, sorry, it's a second. It's second because this is frequency.
R is frequency.
Yeah, it's a rate. So it's okay. S minus 1. So it should be S. And it's just a number.
And L?
Yeah, but yeah, L, these are just constant, right?
Okay. So cost function is time.
Yes.
And this C prime is according to the velocity.
Yes, exactly.
Universe velocity.
Yes. It's no, it's a velocity, right? It's S all over.
And shall I compare? What's good? What's bad? With which velocity I have to compare it? Light velocity, sound velocity,
no,
velocity.
We have to compare it with the velocity of other protocols. It's not important here. So of course the rate is easy to understand, right? Something is faster than the other stuff. Here basically is telling you that the lower is this cost function, the better. That means we are using, so for example, you can fix the rate, so a certain value, and you say, okay, to reach this value, how many resources do we need? You can think of it like that. So you fix, for example, you want to say, we want to change a 1 kilobit key, 1,000 bit secure bit per second, sorry. How many resources do we need to do this? And that's so basically the cost function will tell you. So in this case, if you think about like that, the lower the better. So we want to minimize this quantity.
So the rate is like number of shared entangled pairs that could be considered safe.
Yes, exactly. That's exactly the definition of the rate.
Okay.
In fact, the rate actually could be, not in this case, but there are other terms, depending on the protocol that you're using, that sometimes it can give a negative quantity. But it doesn't make any sense, right? But in that case, it's zero. That means you can still have you can still share bits, but they're not secure anymore. Okay. So normally this quantity, as I say, they're not in this case, but it could be, so it's actually the right definition is the maximum between 0 and something bigger than 0. Okay, so that means 0, of course.
Because this H is bounded by log of 2, right?
Yeah.
So that's larger than 1.
Yeah. So to be honest, this is just the rate that we are using for the protocol that I'm going to explain. Normally, you have to think of these as, of course, like you can think here like errors that you have. So it's something depending on the error. In our case, we can substitute this error with the total fidelity in our system. But it's something, of course, that related to the errors, because always there will, as I say, in the QKD, basically what happens is that people say, okay, for example, this detector is not perfect, or this memory is not perfect, so we just plug the errors, and the error will contribute, of course, to the total fidelity, right? So you can still share your entangled state, but the quality will be so bad that Eve can have information about that. So conceptually, that's what is the rate. So after this long introduction, let me go to what we did. So what we did is basically, I didn't want to put many mathematical formulas, but that's actually what the type of codes that we are using. So we are using, in our protocol, we are not doing quantum purification. Okay, let's start from that. So that means we are doing quantum error correction, right? And the way the logic state that we are using are defined in this way. These are called the rotation symmetric bosonic codes. And this is the definition. So we define the zero logic as a sum of the rotation operator applied to this theta, which is basically, we call it primitive function. If you want to just think of, for example, coherence state alpha. Here is the example. So if you, for example, put here alpha and you do n equals 2, you will get your cut state, alpha plus minus alpha. And 1 will be I alpha plus minus, so basically it will be rotated by pi over 2. Of course, you may ask me, you can ask why are we using this state? I will show the benefit of using the states in the next slide. But what is important here is that we are using, this type of state, which are basically, these are states, are eigenstate of the rotation operator. So if we apply basically rotation operator to 0 and 1, we get the same state. And so why these states are important? The states are, by the way, this is just some example. So we can have, for example, depending the primitive that we put here, right? We can obtain a different type of states. For example, the cut state, if you put alpha, or the squeeze cut state, if you put a squeeze state, the binomial code, or the Peck-Barnett, which I'm not that familiar with that, but we find out, the PhD student find out that our protocol applied to this state is really bad, so I'm just gonna, not consider this one. And then, so these are, for example, some other mathematical definition. In the case of squeeze state, as I said, we put a squeeze state here and here. In the case of the binomial codes, we put this type, this will be the type of encoding. And also we use another type of state called GKP-like. GKP is like famous error correction code, where basically we have this type of state weighted with some coefficient delta. Nicoló?
in the previous slide, the thing that you showed, those are quadratures of Wigner functions.
Yes. Yes. These are just examples of the different type of of these rotations multiples that you can get.
Sorry, can I ask a question? So you said some of those primitives were good and some were bad by looking at those Wigner quadratures of Wigner functions.
No. Sorry, this is just an example of not by looking at the. No, sorry.
No, so you said that you are not going to consider some of those primitives, and how do I understand?
I was not very clear. Sorry about that. What I wanted to say is that we analyze all of them in our quantum repeater protocol, and we find out that the probability, when we use this type of state, we find out that the probability is very, very low, the probability of success. So the rate is also very, very low. I can't remember right now, it's about maybe 10 to the minus 6 or 10 to the minus 7. That was the
so you have to calculate the rate.
Yeah. No. From that, unless you are, I don't know, like super smart, but we have to go through all the calculation before. Yeah. Sorry. Okay, so these are some definition, and basically, I mean, I just put these slides to, although I'm not an expert on that, but this is basically the physics behind how we can create these states. This is the work done here in this. I put the reference here. Basically, the way it works. So the main concept here, as I said, we want to create this state, right? We want to see how this state could be created. For example, cut state, which is the most simple one. So the physics behind it is like we have trapped the atom into a cavity, and with this energy level configuration. So we have that the transition up to the excited. So we have two ground states and the excited state. So the up to the E is strongly coupled to the bare cavity mode. The other one, the other ground state is decoupled from the cavity mode. And basically, and then what happened, as you can see here, we just inject, when I say we didn't do this experiment, but what has been done already, and also I will show you in the final slides that this has already done. Basically, the way they did it was to inject, for example, the alpha, in this case, the primitive that I called, and then depending which interaction, so interacting with the up or with one of these two ground state, basically what happened is that interacting, for example, with the up state, the frequency of the cavity mode will be detuned from the input light. And so this means that basically it's like it doesn't see the cavity. It's like it works like a mirror, and it just stays the same. Nothing happens in that case when alpha is interacting with the up. On the other hand, when it's interacting with the other ground state, basically what happens is that we can get a pi phase. So that's the way we can create this state. What it's important here is basically, so if you do the math of this system, you find out that the out mode will be linked to the input mode in this way, where delta is the tuning, and this corresponds to a rotation operator with basically with the angle phi given by this quantity. By the way, this is just an ideal approximation. The actual when they did the actual experiment, you have much more complicated terms that makes your reflection not perfect. But the ideal case, I mean, what we need for our protocol is basically this relation. So when it's interacting with one ground state, we get this extra phase. So in other words, what it means is that you can tune this delta in a way that you can have the desired rotation that you want. And so let me tell you how you can, in this case, we can generate our state. So from that, you can see that we have that when our primitive is interacting with the up, nothing happened. When it's interacting with the other ground state, we get a rotation. So we can prepare our atom in this superposition. And then and we inject the alpha. We inject our coherence state, right? And we get this, this should be alpha, by the way. But, I mean, you can think of just any primitive. So you get this state. And then what you do, you measure your matter qubit, okay, in the x basis. That means doing so. Measuring the x basis means doing a rotation, right? So basically, the up will become a up plus down, and this up minus down. So depending of the outcome, so this could be measured, and you get basically you can get this state or this state, right? So you measure this part, and you get your photonic contribution. Again, you can prepare another cavity, in this case with pi/2. So you tune your cavity in a way that gives you a rotation of pi/2, and you can create a more complicated state. So in this case, the state will have, for example, this contribution and this contribution. Just a
question.
Yes.
In the middle line, when we're writing measuring in the x basis.
Yes.
So there the primitive plus that down thing, is that correct? Or
yes, it's the primitive plus this down r pi, because we decided to put it in the pi, tune in the pi.
I thought you were writing the matter qubit and the primitive part separately, no?
Yes, you're perfectly right. And I think, yes, forget about it. This is not, you're right.
Okay.
This is not here. Sorry about that. Yeah, of course, it doesn't make sense. I mean, if you look at it, yeah, anyway, that's a mistake. This is not part of the thing. That's why I hate equations, because I always make mistakes with it. But anyway, yes, you're perfectly right. This is not here. So of course, when we measure x, we can get this state or this state, and this will project into this or this. So this is, the final result is correct. But this is wrong.
So may I get a little bit of context? So now you are talking about preparing different types of entangled states.
Yeah.
So you can study how well they perform on these quantum repeaters.
Exactly.
Okay.
I mean, as you can see here, we, as I said, our goal is to create this encoded state, right? And I'll explain you in the next slide why we want this state. But here is just to show you that at the end you can do repeat this process as many times, always doing the rotation angle half. At the end, you will get basically this entangled state. Now, this is an entangled state, so you will have your up, which will be coupled with the zero, we call the zero, and the down with the one. So that's and this is valid for any type of rotation bosonic code that I explained in the previous slide. Okay, so this is quite general result for this type of code. So that, I mean, as I say, why this is good. This is good because in quantum communication, we have to address the main error that we want to get rid of is the loss error. And this kind of allows the property of this type of state give us an opportunity to cure this type of errors. And I'll show you an intuitive picture of how this could be possible. And this is possible thanks to this so-called quantum measurement or also quantum non-demolition measurement. So let me show this thing. So basically, we have our initial state that goes through the lossy channel, which is represented by the annihilation operator. So what it's saying here is that our state is losing Q photons. Let's assume for a moment there is losing Q photons. Of course, this is just a specific example. In the reality, we don't know how many photons are losing. So this Q normally goes to zero from infinity, right? But let's assume for a moment that we are losing Q photons. So that's the way we can write down our state. And then we have the rotation operator and the annihilation operators are linked by this formula. So basically, when you commute your rotation operator with your annihilation operator, you can get this extra phase here, e to the minus iq. So you have this q, which, as I said, is the number of photons that we are losing. Okay, phi. That's something that you can demonstrate quite easily. And then basically what we have here, okay, so remember again these properties, as I say, that this type of state are, the good thing of this state are eigenstate of the rotation operator with eigenvalue 1. Yes, it should be eigenvalue, so with plus eigenvalue. And then basically what happens, so what happens is this, we prepare an ancilla qubit into the cavity. We call it S because it's a syndrome measurement. So the S is for a syndrome measurement. That's just an ancilla cavity. And we tune our reflection angle in this way So if you think about it, if you want to make it more simple, let's say that in the case of the cut state, m is equal to 2. So you have pi over 2 here, rotation. And then after the interaction, so basically what happens is this photonic part reach our ancilla cavity, we get this state. I mean, you can see, because basically what happens is that we have to perform a rotation operator here. This rotation operator commute in this way. So we have a rotation operator will be there. And the rotation operator applied to this state, as I said, is an eigenstate with eigenvalue 1. So at the end, we will have this extra phase, which is given by 1 minus IQ pi over 2m over minus 1. And then, finally, this is telling us already that if we measure now this ancilla qubit, we can actually know how many photons we have lost, depending, of course, of this q, right? So this will be, for example, plus or minus. I mean, maybe we don't know exactly how many photons we lost, but at least we know, for example, if we lose an odd number of photons or an even number of photons. So in other words, basically this type of measurement is giving us information, some information of how many photons have been lost during the transmission. And this allows to, of course, I mean, I don't have time to demonstrate, but this type of measurement, so measuring this state, at the end allows to increase the fidelity of this A, it means like Alice, right? The state, the final state of Alice. Of course, this is not, of course, this is not a perfect thing because, as you can imagine, for example, if you have Q2, the number of photons, we have the same phase, even if, Q2 is linked by the another number of photons by this, in this way. So that means that, there is no way, because the phase, it's a cyclic thing. So when this number of photons is linked, is equal to Q1 plus 2m, we have the same phase. So we cannot distinguish in that case, unfortunately. And also, it's not always possible to discriminate deterministically the atomic state with different phases. So what it means here is that sometimes, when we have, let's say, up plus down and up minus down, this is orthogonal. So we can, when these states are orthogonal, deterministically can be distinguished. But sometimes, depending on the phase, they are not orthogonal. So even in principle, we cannot distinguish deterministically. And to address this issue, anyway, we could perform many of these rotations. At the end, performing many of these rotations, dividing this angle half at each step, we can actually create we can create an orthogonal state. That means we can have, for example, up plus down or up minus down. And this is the reason. This is the reason why we are using these states. Because as you can see here, the source of errors is the loss. And we are kind of knowing something about the loss thanks to this type of measurement. And this property can be given only by this type of state because they are rotational invariant. So that's why they are good. And then now let me show you how we can create actually the entanglement. So the entanglement is kind of easy because as you can see here, we have our entangled state sent by Alice, and Bob prepared his state in this way, right? Like, for example, superposition up and down. And then we tune the atom into the cavity of Bob. We tune it with basically pi over 2m. You can think of pi over 2 if m equal 1. And then what happens is that the rotation operator tuned in this way, basically it works as a, basically is a switch from 0 to 1 and to 1 to 0. This basically, what happens is that if you do basically the math, but it's very simple, what you get is basically you get a type of state that will be given by up, up, and down, and up, down, or down, up. So basically you, by performing these, depending of 0 and 1, so then of course you have to measure either 0 or 1, you will project your final state into one of these two entangled states, of course with this phase. The problem here is that these light modes are not orthogonal. Something that I forgot to tell you is that unfortunately our encoding, so normally in quantum error correction, the 0 logic and the 1 logic you want them to be orthogonal. The reason for that is because at the end you have to measure. So you have to know whether it's 0 or 1. But if they are not orthogonal, in principle, there is no way to tell, if you get 0 or 1, or sometimes you can be both. So in other words, we have to look at the probability of, which basically would be the probability of success, this QUST. As you can see here, it's given by 1 minus the overlap of 0 and 1. So of course, when these guys are orthogonal, the probability will be 1. Unfortunately, they are not, so we have to deal with that. Yeah, so that's so what I'm saying is like these states are nice, these type of states are nice, but they are not orthogonal. And we include this, let's say, this thing here in this, so we have to multiply basically by this probability of distinguish these two states. Or it also could be, the most general formula is this one. And then finally, so yeah, for example, for cut state, you get this very complicated probability of success, 1 minus cosine over cosine interval. Yeah. And then, okay, so sorry, but this is still Alice Bob, but I stole this slide by the PhD student. As you can see, he used different Bob than me, but it's the same thing. So after all this is basically the way we do our repeater scheme. So our repeater scheme is made by two types of stations. We have ES1, which works as an EPR source, and ES2. So ES1 is basically creating the state, let's say, up 0 plus down 1, and sending to ES2. What happened in ES2? In ES2, we perform the syndrome measurement. So we prepare this ancilla in a way that we can increase the fidelity after the channel, so after there is some loss. And then we do the entanglement creation, which is what I showed you in the previous slide. And then after this, so after a series of syndrome measurement and the entanglement creation, so in other words, basically what we have is we are entangling this station and this station. We do the famous Bell state measurement that I talked before, right? So basically we do the Bell state measurement between these two states. In this way, we could extend the distance over and over until we do this Bell state measurement in all this ES2. So at the end, we connect all the S2 until we have Alice and Bob. In this case, we don't need we don't need classical communication, right? Because we don't have any, so we know that this thing will succeed with some probability, of course. In our rate, we are including this probability. So unfortunately, we have to take into account this part. Because this entanglement creation here is possible only measuring 0 and 1. As I said before, they are not orthogonal, unfortunately. And that's the way the entanglement, the repeater scheme works. So as you can see here, we don't need memories. We don't need quantum memories because basically when we create our state, up 0 plus down 1, we can immediately measure this matter qubit. So basically what we create is actually an EPR source traveling this direction and this direction. So we don't need memories. And also we don't need classical communication. That's the good thing of this protocol. And so I'll show you just some results that we got. So, okay, we calculated the security rate versus the elementary distance. And as you can see, we have for all the codes that I talked in the previous slides. And as you can see here, we have, for example, this blue one, which is the worst, is the cut code. And then we have, so this is the squeeze cut code, this is the GKP, and this is the binomial. So the binomial is actually very, very good compared to the others. The reason for that is because the probability of success, as you can see here, it's quite high. So the binomial code, has the property that the states, when we do the encoding, basically the states are almost orthogonal. And even during the channel loss, they basically stay orthogonal. So that's why the probability of success is very high. In the other case, it's super low because the orthogonality is like really bad for example, for the cut state. And you have to think that the probability of success should be calculated in each elementary link. So you have probability of success for each elementary link. think about it over 1,000 kilometers. For example, here, if the elementary distance is 1 kilometer, we have 1,000 stations. So you have to do the exponent of the probability of success to the 1,000. So if it's even slightly less than 1, it will go really, very low values. But at least the binomial is good. So as I said, what is important here is to calculate the cost, coefficient. So for this repeater, in this case where we are using binomial code, we calculate the cost coefficient, and we got this versus in this case the total distance. So in other words, in this case we assume that we want a cost coefficient of 100, and we see how basically the elementary distance is changing with the total distance. The reason we do this is because we want to compare with other protocols. And we find out, although I'm not showing the comparison with other third generation quantum repeater protocols, we find out actually that this distribution of points is quite very similar to other repeater protocols, but the other repeater protocols always require very complicated error correction codes. So at least in our case, it's not it's not super complicated. And finally, basically, yes, this is basically as I say, it's the success probability versus alpha versus, if you think about it, it's like the average number of photons for the cut code all over a distance of 1,000 kilometers. And what you notice here, you notice two curves that goes almost to 1, and this is not exactly 1, it's almost 1, the probability of distinguish the two states. So this is telling us that for some values of alpha, we can actually create orthogonal state. However, the problem, what is it? That we have to perform this syndrome measurement. So the syndrome measurement, sometimes, for example, we get one value, and we are here. Sometimes we get another value, so we are here. So at the end, we have to kind of do the trade-off. Which alpha do we use? What's the number of average number of photon we want to use? We cannot use only this, we cannot use that, so we have to use one in between, and that's the reason why the probability of success is very low for this case. Basically, to address this issue, we use we might think of using quantum memories. Yeah, sorry, I said we are not using, but let's assume we can use quantum memories. To do that, the reason is because basically, if you use let's say if you use multiple channels, so instead of having only 2, we have many. You can think of more channels. We can actually distribute these, so we can entangle our photonic state with the quantum memory, sending it to the ES2 station, and then we say, you know what, this syndrome measurement and this syndrome measurement is the one that we like. Okay, so ES2 will tell ES1 what are the syndrome measurement we are looking for. And so he will perform the best measurement between these two memories. Because as I said, so that's the reason why we need memories in this case, because we have to wait for the classical communication from ES2 to go back to ES1. No, it's bad, but we need quantum memories in this case. And another way to do this is using cluster states. Cluster states are actually feasible, and basically a cluster state is in this case is a photonic cluster state, where each of these photonic state is entangled in this way. So, for example, this one. So it says there is a way to create these cluster states. Of course, I don't have time to go into details, but we can make this cluster state with some efficiency. And the good thing of this cluster state is that now we can use them instead of quantum memories. We create the cluster state on ES1 and then propagate to ES2. Okay, so what? Again, for example, this one and this one, we do the syndrome measurement. This one and this one, so all we do the syndrome measurement, right? In all of them. But this one and this one are the syndrome measurement, the outcomes we are looking for. So we perform a Z measurement of these, because these are, let's say, the bad ones that we don't want. And the effect of doing the Z measurement is to eliminate, basically, to cancel this state from the cluster state. So at the end, we'll have these two entangled states that can be used for distributing entanglement all over the distance. So with this simple trick, we can manage to also use the so with this simple trick, let me show you. So as you can see here, the probability was really bad because we were using alpha in between. But now we can just choose, for example, all the outcome, we can use an alpha, for example, these values here, that correspond to a specific syndrome measurement. And we can do this because we are choosing, okay? So this guy basically say, okay, the syndrome measurement is 0. Okay, let's keep it. And the same here. This syndrome measurement is good one, so we keep it. So now we can use that specific alpha that give us the maximum probability of success. And in fact, thanks to that, we can have a very high key rate. So now this key rate is the same one that I showed you before for the cut state, but before was less than much less than 1. Now it's it could reach even 10 to the 2, and even maybe higher values. So in this case, the key rate is much better using this method. And then basically something that experimentalists are, they want to know, okay, but what's the coherence time of these memories, or what's the gate efficiency when you do clusters, when you use cluster state? So coherence time and gate efficiency are two things that we have to look at. We have to look at it basically. There's nothing we can do. So here basically we plot the gate inefficiency 1 minus p. So the gate is better when we go down versus the coherence time. So as you can see here, for example, the better is the gate. So the better is this guy here. The longer coherence time we need in the memories. So in other words, basically we are comparing this system and this system. And to do this, we have to compare the gate efficiency and the coherence time. And then we obtain this kind of flat region that is, again, it's very important result because it's telling us when we get flat, what it means. It means that higher coherence time are not important. So why do we need, for example, coherence time 1 hour when we can reach the same result with lower coherence time? So that's why this type of graph could be interesting for experimentalists.
Nicolò,
yes.
5 minutes, okay?
Yeah, I'm done.
Okay.
That's basically so I put these slides to show that thanks to this system, we can also increase the rate using cut code. And the reason we want to do this, because as I show you, cut code is kind of easy to create in laboratory, that's why. So yes, and then let me first, finally, that's actually the very last slide, let me show you that actually this type of encoding has already been experimentally done by Gerald Rempe. I can't remember when this paper was, maybe 3 years ago, but I'm not 100% sure. So basically this graph, again, these are the big grand function, Gabriel, if you like, and they found this big grand function that basically is showing that they can create, so it's exactly the same procedure that I explained you before. They do so you have this atom into the cavity, they do the rotation of the atom, so they create the up plus down. They do the interaction with alpha, and at the end they create either the odd or the even cut state. Again, they measure into the X basis, which is the slide that I made a mistake, basically, and you can get either the odd or the even, the odd or even cut state. So it's already done, basically. It could be possible. And again, you can use this state and with another cavity and create more complicated logic states, as I showed you before. And these are the rotationally, they have the property of being rotationally invariant. And this is basically the truth table of this atom cut gate. So basically, as you can see here, for example, if you have up plus alpha, there should be, let's say, 0, 0. So this is a C0 gate. Okay, so they implement a C0 gate. So for example, if you start with the down plus alpha, you end up with down minus alpha. Okay, and the fidelity is quite high. I mean, 86%. So it's a good experimental result that, as I said, could be used for them implementing the protocols that I described to you. And then, I'm sorry, that's, yes, and then thanks for listening. These are beautiful pictures of the beach in Okinawa. So please, if you want to come and visit us, you can also enjoy the beach and the sun. Yeah, thanks a lot.
Okay, do we have questions?
Okay, I will have one question. How far are we with the creation of quantum internet? Do you know time scale?
You don't have to ask me this question because I mean, how far? As I said, in Delft, right? Delft, they were supposed to make something already 3 years ago, but as far as I know, there's nothing actually done. The main issue for a quantum internet comes from basically the error correction codes that you need to protect your state are not mature enough for the task they want to accomplish. So, for example, this gate efficiency that I talk about is actually the main obstacle to that. Because if you think about it, what these guys did in the experiment is actually doing a gate, right? A C0 gate between the matter and light. And the fidelity is 80–60%, right? Maybe for some application, you need the 100% fidelity.
So the time scale is the same with fault-tolerant quantum computers.
Exactly. Yeah, okay. Exactly. Fault-tolerant quantum computation is actually the main building block of a quantum internet.
Thank you.
Okay, if there are no further questions, then let us thank our speaker again.